Welcome everybody to today's webinar. Whether you are already very familiar with 𝗪𝗪 current or just beginning to explore it, we are very happy to have you here together with us. And we are very pleased to see such a strong interest in this session as we have people from different regions and different disciplines, designers, engineers, integrators, and operators. So it really reflects this kind of growing momentum around 𝗪𝗪 current systems. Okay, now we have 67 joiners already. So still 1 minute and we can start. Okay, so maybe you can start now. So first, welcome everybody to join this Mastering Electrical Protection LVDC Microgrid Insights from Asia-Pacific Applications, brought to you by Current OS. We are very pleased to have you join us today. We have our speakers, 𝘁𝗁, Power System Expert, Electrical Power System Competence Center for Schneider Electric. Welcome. And we have Roland 𝘁𝗁, Standardization and System Architecture Manager for Eaton, and Marco Camenetti, PhD, Thought Leadership Senior Principal Architect, New Electric Distribution for Schneider Electric. And I'm Dory, R&D Manager in China for Smart Power Division, Electrification Business for ABB. And I will be the moderator for today's session. Eaton, Schneider Electric, and ABB are all valued partners for Current OS, and we are all committed to the application and the standardization of 𝗪𝗪 current devices and systems. And we are also joined by 𝘁𝘁𝗂'𝗹𝗹, General Secretary of Current OS, and 𝗪𝗪𝗿, in charge of Current OS marketing activities. Yep. Before we dive in, just a few housekeeping notes, and feel free to ask questions by any time during this session. And we have dedicated time for the discussion after the presentation. And your microphone and camera are turned off. If you would like to join us, let us know in the chat, and we will invite you on the stage. And then second one, the webinar is recorded. All the registered participants will receive a YouTube link and a replay link accessible from China. You can also follow Current OS, LinkedIn, and YouTube to stay connected with this DC community. So if you are in China, maybe you have some difficulties, then maybe we can meet in the ICDCM in June in Xi'an, organized by Dr. Ni. Yeah, we will thank for her support. Okay, then to be started, I would like to briefly explain why Current OS was created. So our world is electrifying, and we are living through what experts call the largest mass-scale electrification change since ever, and our world is shifting to two fundamental ways. First, we are transitioning to renewable energies that generates direct current by power solar panels, by batteries. Those all generate direct current. And also in another side, we are moving to an all-electric society that consumes direct current. All the modern appliances are using direct current. For example, our cars, computers, data center, LED lights, smartphone, all run on DC. Yet infrastructure still dominantly AC-based. Because of this, DC is increasingly recognized as key enablers for efficiency and energy access. As the IEC notes in a 2024 report, direct current can fundamentally improve energy efficiency and system performance. However, there is still no global distribution framework allowing DC source and loads to be interoperable seamlessly. So this is a gap what Current OS addresses. Yeah. Current OS is a global non-profit partnership over 120 manufacturers and electrical stakeholders. So working to shape the interoperable DC distribution standard and enable certified DC products and systems. So this initiative promotes electrical safety, energy resilience, and the energy transition. This partnership brings together industrial leaders, manufacturers, integrators, and universities, certification bodies, and also even trade groups across North America, Europe, and Asia Pacific. This ensures both technical in-depth and also global applicability. APAC is a very dynamic region for direct current. We have a lot of industrial innovator and also policy momentum in this field, and many active partners already contributing the deployment and also the standardization. So for example, you can see here in China, we have Green, Hisense, 𝘹𝗵𝗿, and also winning as industrial players, and also very well-known university as xi'an-jiaotong University, Shanghai Jiaotong University, and Nanjing Aerosonic University. And also we have players from Japan as Fuji Electric, Nikko, and also players from Australia as DC3 Data, and also World for Solar, and also universities from New Zealand as Waikato. So this reflects a very dynamic and different aspect of this DC community. Yeah. So the core principle for current OS is learning from the real cases, from real deployment. This slide shows a lot of different applications across the world, and in different application in building mobility infrastructure and also the energy systems. So we can see from the EV charging, from the residual building, commercial building, campus, and also energy storage, microgrids, and so on. So these projects shows that DC is moving from pilot projects into operator systems across different regions. Today, we will explore such a deployment in depth also. A DC factory in China illustrated how proper LVDC protection architecture and are implemented in practice. Okay, now let's dive into the heart of our topic today, mastering electrical protection in LVDC microgrids. So Roland, please take it over.
Yeah, we'll go to the next slide by then. Welcome to everybody in this webinar on DC electrical protection. My name is Ronald Niehoff from Eaton, based in the Netherlands, and I'm happy to tell about the current OS protection principles for DC prosumer electrical installations. Let me start by explaining the difference between passive and active DC grids. Passive DC grids are the traditional technology since decades. The characteristics are no power management, the voltage sources are direct connected to the DC circuit, there are protection devices like fuses, circuit breakers, there is a centralized radio architecture, there is a high fault energy and a high arc risk, and they are often used in special industrial installations like control circuits or supply of critical systems. The picture shows a screenshot from a movie about arc flash, and as you can see, there is a quite huge arc when you open in a traditional DC circuit a mechanical contact. But since technology moves on, it is also now possible to have such applications done with electronic converters. So active DC grids have totally different characteristics. The power management is done by group control or communication. The sources are connected only via converters. The protection is based on semiconductor circuit breakers, and it's used in all types of installations. And you can manage radial, ring, mesh, etc. There is a low fault energy and a low arc risk. You can use it everywhere you like. The block diagram on the right side is a picture from the IEC 63664-S-82 Amendment 1, which is a DC prosumer electrical installation standard, which will be published in the coming months. It's the work of IEC Joint Working Group 44. The AC version was already published. The DC version will be published in this year, in the coming months. The picture in the middle shows a short circuit flash at a 700 volt 70 kilowatt zone 3 cable, and I will come back on the zoning system later in this presentation. It's part of a movie where you can see that the arc flash risk is very low as soon as you go into zone 3. Nah. Hello, am I back in the room now?
Roland may have some issues for network.
We can hear your voice.
Yeah, can you hear me now again?
Yes, we hear your voice. Maybe your image will come back soon.
Yeah, I will continue then my presentation. What is the future of DC grids? In the upper part, it is shown the situation now. We have only high voltage DC transmission between continents, but the lower part is the future situation, where DC is moving from high voltage to more medium voltage applications, but also from low voltage applications into the medium volt applications. And how will it work? How will future DC grids look and how do they work? Oh, I have to take the next slide. Yes. Active DC components are on the low voltage and medium voltage level. Protection and switching is mainly done by semiconductor circuit breakers, and energy balancing is on local level area, so inside of the active microgrid. Both off-grid and grid-connected operating modes are possible, and with local renewable and storage, it is possible to supply also HV and medium voltage grids. So also low voltage and medium voltage grids support each other. But there are also a lot of other advantages on active DC grids. For example, the use of copper. It's much less copper need for a DC grid, for an active DC grid. It is much more difficult to sabotage the whole high voltage and medium voltage grid. And there is no sensitivity for internet attacks. And it's simple, manageable on a local level. With the infograph on the right side, it is a picture from an article from the New Scientists from 2007 already, and is showing how many years we have left for our key natural resources. For example, copper is expected to be available between 38 and 61 years from 2007 on. And you can see that the DC active grids can help a lot in saving copper. About the general DC grid design. The right picture shows again the picture from the IEC 60364-8-82 Amendment 1. But the content of the IEC standard will be very generic. It gives safety recommendations, but no explanations. Left picture is from the CurrentOS installation rules working group, and CurrentOS will provide in much more detailed explanations and requirements for technical topics like the wire selection and the loop impedance. But also, besides of that, CurrentOS also gives technical paper information. Technical paper, for example, of how the fault protection is done in the zoning system, in zone 3 installation, in zone 3 of your system. And that is shown in the picture on the right side. Then about the zoning concept, which is a quite important part of the CurrentOS set of rules. The protection rules are strongly linked to the DC zone. You can also find some more information about it in the MOOC on the CurrentOS YouTube channel. There are 6 videos about all types of aspects on active DC grids according to the CurrentOS set of rules. And part 4 is about the protection and DC zones, which are explained into more detail. An installation can be subdivided into several zones, zone 0 up to zone 4. And I will explain in the next slides what is the zone. DC zone 0 is the most dangerous zone. This is the zone which is connected directly to the source without any protection. It's the highest risk and the highest challenge. There are only physical barriers. If there is an accidental contact, then there is immediately a high risk. For example, an explosion with injuries or fatal destruction. If maintenance is needed, personnel need to have protective clothing. A typical example of such a DC zone 0 is a battery rack. So without already the first level of protection. If you go to DC zone 1, then there is already a first level of protection between the source and the distribution. So for example, an electromechanical breaker or a fuse with a typical breaking time of less than 50 milliseconds. There we are in DC zone 1. The fault hazard level has become much lower already, but still there is a high risk for explosion and people need to wear protective clothing. So a skilled environment where only maintenance crew can attend. The typical area where zone 1 is occurring is in an electrical cabinet in a distribution system. This is zone 2.1. Again, there is limitation of the energy in case of a fault or short circuit. There are current limiting converters in this area, and there are electromechanical circuit breakers like just the mechanical versions or fuses. There we are in zone 2.1, and the risk is already again lower. There is a small arc flash, and the technician is shaken but not much injured. There is special clothing needed, but again, not so severe as in the previous zones. And the typical area where DC zone 2.1 occurs is in a solar panel installation. In DC zone 2.2, there are even less energy in case of fault and in case of a short circuit, because there are hybrid circuit breakers. Hybrid circuit breakers have a typical break time of less than 1 microsecond, milliseconds. If there is a fault, there is a small arc, but it's very limited. The energy for maintenance crew is lower, and protective clothing again is not so severe anymore. Typical areas where such DC zone 2.2 is used is in the coupling of DC generators inside of a factory, so in the distribution area. And my last slide is on the DC zones 3 and 4. That is the area where current OS is really focusing and this is again a really low fault energy area where semiconductor circuit breakers are used with a typical break time of less than 10 microseconds. So if there is a fault, there will be a very small arc and there is no high incident energy involved. There is also the possibility to prevent for direct touch. So personal protection is also possible. The maintenance crew does not need to have special clothing because it's actually an unskilled environment. And the typical use of DC zones 3 and 4 is actually offices, commercial spaces, residential areas as well. So actually everywhere where there is a need for DC. Thank you. That was my part.
Thank you, Ronald. Good afternoon, everybody. I'm Marco Carminati, Senior Principal Architect for Leadership in Schneider Electric. Let's talk about now about the protection rationales and interlink converter behavior during a DC fault, both short circuit and ground fault. So first of all, AC and DC network do not behave the same. As you can see here in the figure, AC and DC network can be represented in two different ways. In an AC network, we have basically a series of the cable inductance and of course resistance, plus the big inductance of the sources, like for example, synchronous or asynchronous generators. Instead, in a DC network, we still have, of course, the inductance during, in particular, the transient phenomena of the cable with the related resistance. But because of a lot of AC-DC and DC-DC converter interfaced with the DC distribution network, we have a lot of capacitances. So, as you can see, in AC, we have basically an LR network. In DC, we have a RC network. So in AC, sources inductance is much higher than the cable inductance, of course, while in DC we don't have, or the source inductance is very, very low lower compared to AC. So in AC, we have a very high impedance in the fast time domain, unlike in DC where we have a very, very low impedance. So we can have a very fast transient phenomena, in particular regarding the variation of the current. Indeed, in AC, we have a large reduction effect of the fault current derivative, while in DC, we can have a very high current derivative. And we will see that it will affect the selection of the protection devices. So in AC, historically, electromechanical protection devices were and are still effective, while in DC, protection devices must be very fast to limit the current and to protect, in particular, the semiconductors of the converters. So in DC, solid-state circuit breakers are more effective than historically in AC, where they were not needed. So next slide. Now let's talk about the fault stages, because in particular the fault stages can lead to the definition of several ILC, so interlink converter categories. Whenever we have a fault on a DC side, either a DC short circuit or an air fault, basically we have three fault stages. The first one, the fault stage one, is the first stage which appears during a fault, and it is a very fast transient component due to the converted DC capacitance discharge. The transient phenomenon, of particular the current, can be overdamped critically damped or underdamped. Basically, if we have or not an oscillating waveform of the current. In particular, if we have an underdamped phenomenon, we can have also the fault stage 2 because the voltage on the capacitor can become negative. And in the fault stage 2, it is still a transient component due to the current flowing through the freewheeling diode of the interlink converter. The first stage is affected basically by the ratio among the inductance, resistance, and the capacitance of the system. Fault stage 2 can be present or not. And finally, we have the so-called steady state stage, the stage 3, sorry, which is the basically contribution coming from the AC part, which can be present or not according to the architecture of the converter. So in the first category of a converter, we have basically the non-isolated ICDC converter, as you can see here in the picture. So the first category of converter are able basically to limit, are not able to limit the contribution coming from the grid. So if we have a medium voltage, low voltage transformer neutral, which is earthed, and the DC system is unearthed, there is basically a DC fault current passing through the converter. So even if the DC is isolated, we are not in a real IT system because we have the current circulating from the neutral. Instead, if the DC part is grounded and the neutral of the transformer is ungrounded, I remind you that we cannot connect both the active part towards ground in a non-isolated converter in order not to create an internal fault. If we have the DC part grounded, basically it's like to have a short circuit on DC side. So basically all the stages of the fault are present in this type of converter. In the second category of the converter, as you can see here in the figure, that includes the so-called isolated converter, whose architecture is made by a combination of non-isolated converter plus a dedicated low voltage external transformer, which is not the main transformer of the system, is a transformer dedicated to the converter. So if we consider the sum of these two components, we have a sort of isolated converter. And they are able to limit the fault stage 3 in case of a medium voltage, low voltage transformer neutral earthed, and a DC side unearthed, or we have a midpoint earthed on DC side. In this case, we can connect both parts towards ground because we have an isolated transformer. But they cannot limit the fault stage 3, so the contribution coming from the grid, in case of DC short circuit or an air fault on DC side with an earth DC polarity, for example, the negative. In case of a DC short circuit or an air fault on a DC side, let's say all the stages are present because, let's say, in this case, the transformer can isolate but cannot limit the current passing through it, in particular the transient current or the IC current, of course. In case of a DC air fault with a medium voltage, low voltage transformer of neutral and unearthed DC side, we don't have the fault stage 3, as of course the direct current cannot flow through the transformer, in particular through the grounded neutral. But the fault stage 2 and 3 are very, very small, and due to basically the small capacitance between the primary and secondary windings of the transformer, but basically they can be considered negligible. Last but not least, third category basically includes isolated converter with an internal high frequency transformer. In this case, we're able to limit the contribution coming from the AC grid, so fault stage 3, in both cases of short circuit and air fault. In case of a DC short circuit or air fault with an 𝘃𝗍DC polarity, fault stages 1 and 2 can be present. So the transient phenomena can be still present, even if we have an isolated converter. But we don't have the contribution coming from the AC grid, basically because the inverter stage inside the converter, so the stage before the transformer, is able to limit its, let's say, basically AC contribution to the fault. In case of a DC air fault with a medium voltage, the voltage transformer earth neutral, and an unearthed DC side, the converter behavior basically is the same of the category 2, basically, so we don't have a fault stage 2 and 3. So, according now to the several categories of the converter, in order to protect also the converter themselves, but not only the converter, just because also the architecture of the DC network, so basically an RC system. When we select a solid-state circuit breaker in a DC distribution system, we have to follow a different criteria instead of the traditional criteria we use to select a traditional electromechanical circuit breaker. Because in AC, but also in DC, we select the breaking capacity of the electromechanical circuit breaker according to the so-called prospective maximum short circuit current. If we have a solid-state circuit breaker, we don't have to select according to the maximum, let's say, current, which will be expected to be in our system, but we have to take care of the derivative of the current because of the very, very fast interruptive time of the solid state. In particular, the derivative has to not exceed the maximum admissible value declared by the manufacturer. So during the limitation time of the solid-state circuit breaker, the current has to not exceed the maximum value that the semiconductor is able to interrupt, semiconductor inside the solid-state circuit breaker. On the other side, the circuit inductance has to not exceed the maximum switchable inductance declared by the manufacturer. So basically, we select a minimum value of the current derivative because, let's say, the higher the inductance, the higher the energy which has to be handled and dissipated by the internal, basically, clamping device of the solid state. So in a solid-state circuit breaker, the derivative, current derivative, define the short circuit interruption performance more than traditional rated ultimate short circuit breaking capacity called ICU. Next slide. So according to the several zone description made by Ronald, if we focus on zone 3 and zone 4, they are usually safer than traditional AC installation. Why? For several reasons. Some of them are here shown. First of all, because in zone 3 and zone 4, we use very fast circuit breakers, solid-state circuit breakers. So the breaking time is very, very fast. We are talking about tens, maximum hundreds of microseconds. So the related fault energy is very, very, very low. And if we have a very low fault energy, also in case of arc flash, usually the incident energy is lower than 1.2 calories per square centimeter, which means that we don't need any PPE inside zone 3 and zone 4. Nevertheless, RCD are still possible for long distribution cables as a fault protection or also as additional protection against direct contact. In particular, in current OS, we are, let's say, working in order to have a certified equipment for interoperability and safety with a dedicated certification scheme. Last part of my presentation is dedicated to the earthing system in DC. In particular, let's focus on DC system with isolated converter. We can still have the earthing system like in AC, but unlike in AC, not all of them are recommended. In particular, if we have a TT system, so basically the active part are grounded and also the post-conductive part ungrounded, these systems are not recommended, not only by current OS, but also from other DC communities like ODCA or Emerging Alliance. Why? Because the stray leakage current are not directly redirected to the source by a continuous P, of course, through the ground. So this phenomenon can introduce a voltage drop, and if it is higher than 200 millivolt, according to the standard EN 5162, we can have corrosion, steel corrosion effect, and the result is it is better, it's strongly recommended not to use a TT system, unlike in AC, which it is quite common. The same for TNC or TNCS system, as the exposed conductive part are connected to the so-called PEM, a conductor which includes basically the function of M conductor and the PE. Why? Because also in normal condition, load current flow through the PEM. And as a result, we can have a voltage drop on the PEM, which can be still higher than 200 millivolt. So also in this case, that could be the risk of corrosion. So in current OS, and this is my last slide, we have and we recommend either TNS or IT system, in particular TNS system. As you can see here in the figure, we can have either a unipolar or bipolar system according to the voltage towards ground. A unipolar system is 1 voltage, bipolar double voltage or 2 voltage towards ground. Of course, unipolar systems are easier to be implemented with no asymmetry, and usually only a single pole overcurrent protective devices can be used, while bipolar, of course, are more flexible. We can have 2 voltage in the system, but they require a more complex scheme, in particular to handle the imbalances of the voltage if we have a unbalanced system, in particular unbalanced loads, and usually we need a 2-pole overcurrent protective devices. In current OS, let's say, we recommend that fault and disturbance on DC side don't affect the AC side and vice versa. For that reason, we recommend to use an isolated converter, and so the system shall be galvanically isolated from the AC grid, and also if we have the midpoint shall be grounded. IT system, let's say, can be used for special application where service continuity is important in case of a first ground fault, but only in skilled environment, and it will be elaborated in the next edition of the current OS system reference document. That's all from my side, and over to my colleague Qiwan.
Thank you, Marco. Can everybody hear me? Yeah, so thank you, Marco, for digestion on DC protections. So my name is Chu Yuan. I'm from Schneider Electric, China, and my current role is a technology expert for DC adoptions Myself, background is about electrical power engineering, and I'm myself is also a early DC adopter across different industries for marine onboard DC systems, and also data center power distribution, and now on DC microgrids for building applications. So today I'm glad to share with you a recent case, a pilot case, which we did in Schneider Electric Wuhan site. This is the manufacturing site, and this is a complete DC microgrid within a building complex. So we did this almost several years ago, and now we're able to, or I'm happy to actually share with you some of the experiences of running COS-based systems, since this installation is set up based on the current OS principle. Behind the shadowed background is actually a panorama view that you can see for the actual environment of the building complex. In the middle there is an office building, and around this office building we built this complete DC microgrid. So we brought a little bit further away from the AC main electrical room. So this is the electrical room for the entire site, and this is a huge site, I can tell you. The distances from that AC main electrical room is quite significant. And by during our design of such a DC power of the DC microgrid, since we are to consume as much as possible the local renewables that is coupled to the DC microgrid site. So around the office building, beside that, you can see an outdoor parking area where we have newly added electrical loads. And this is, of course, everybody could imagine that nowadays you have a lot of EV electrical vehicles that you drive. Here there are really a lot of newly added EV chargers, and we couple it to a 700 volt DC bus, which is a voltage that is presented in the current OS principle. Down there you see pictures of actual rooms in a typical building environment. We have office rooms, we have exhibition halls, we even have a recreation area, a small coffee corner there. And then we have along the parking area along the streets, there's around 100 to 200 meter pedestrian walk. There is street lighting also. So across all these environments in a building complex, we have these typical DC loads coupled with DC sources. And in this case is the rooftop PVs on the office building. So by walking around this panorama view, I wanted to share that with you, that the source is planned, and also the DC loads are also planned in this complete DC microgrid. People, I usually get questions, just one second. Yeah, so I usually get questions about, hey, how would you find loads typically in DC? This is the common question we do have. But in this case, I wanted to present you some of the reality DC loads that you have. So these are the EV charging, quick answers, EV charging, lighting, USB sockets, and air conditioning units. So here I put up reality pictures that myself took for the site. On the first one that you see along the parking area, we actually have 4 off. In the first stage, we have 4 off DC EV chargers. These are newly added loads in the manufacturing site, and we're seeing more and more. because the electrical vehicle adoption in China, in this region, is growing significantly. And that would be the case for everywhere in the world, basically. And these are really new added loads that make sense, let's say, that make sense to be coupled in DC, especially around this voltage at 700 volt main bus. And the second picture is a picture that's actually my own cell phone, well, older version several years ago, but it's already there, taken in a USB-C socket, which is hooked up from 48 volts. So these little blue boxes, or those are USB sockets, 48 volt input USB sockets that we deploy. This is a receptional desk, and we deployed it in our office rooms, easily supplied within the building. And you can see there, that's my own cell phone and my own work laptop, and it's connected, charging well with the USB-C socket. And per socket, it provides 100 watt based on the USB-C standard. And that's a convenient usage for personnel within the building, and also as a designer for myself. The third picture down there, is a typical small air conditioning unit that runs over 48 volt. But of course, for this case, we didn't really touch upon the main air con unit for the building complexes. But nowadays there are huge big units running at 700 to 700, in between 700 to 800 volt DC main input. I mean, air conditioning units. So these are the typical units that you find, and make sense to be coupled in DC. I'm not saying that you want to couple any loads to DC, but anything that exhibits a higher efficiency or exhibits a longer operating lifetime would make sense to be coupled in DC. So that's my conclusion after selecting and running a lot of these DC equipments. So on the, just a second. On the next page here, I summarize the main DC distribution unit for you. So to have a quick look, we put all these converters and protection units within an outdoor container. This is for convenience purposes. That you can find, you may put a DC coupled microgrid within that room in order for your energy to be locally consumed within the DC side. But there is something that I just want to highlight for you is on the main DC distribution cabinet, which is on number 4 and number 5. These little 700 volt protection units acting as the feeder protection for the 700 volt DC cablings. So they're protecting all the feeders going into the building and going to the EV chargers, for example. So they are really realizing the different DC zonings and fault levels that was mentioned by Ronald and Marco in their previous slides. So these are important protection units that we use and that we benefit from, which is important for deploying a complete DC microgrid. My next page, I wanted to share with you on the main human-machine interface for the complete site. This is a typical energy mix daily that we record during the early days of our operation of this system. So simply saying, if you can refer to the yellow line on the main energy mix diagram, you would see that the energy is basically tuned close to the generation of the PV curves, meaning that such a droop control system is easily set to consume as much as possible the PV energy locally on the DC side. And what's more important is that the load curve, which is, and a majority of them are EV loads, EV charging loads in this case, the loads are actually tuning itself also closer towards the PV curves. So this is the important thing, is that we're not just consuming PV, but we're tuning the energy towards the actual generation of a PV. So this is the added part, and this is the true benefit when talking about DC compared to AC, is that we can really do it in a very simple way in DC without this, the same concerns in AC. So this is an important characteristic that I want to bring to you on this display of energy mix. There are three main aspects that I want to bring it to you. First of all, as I mentioned just on the previous slides, is the easy energy management for DC coupled sources and loads. We do it in a simple way. So in our chargers, in our EV chargers, there are these droop settings based on current OS rules, easily implemented, and it function well for such a destination charging scenario at our site. I want to add some more words here, is that our experience is that the number of the charger points is more important than the power level of a single charger. This is very important for a destination charging scenario, and is also important for the DC coupled microgrids. And we were happy to see that after the installation in our Wuhan site, we were able to receive or attract more customers. And now our charger are running basically fully, and there are opportunities that we would need to add more chargers. And it runs basically on renewable energies, and it tunes itself naturally for this destination customers. Right, so this brings a huge, very high consumption rate of renewable energy in our protection coordination. So as Marco and Ronald was mentioning, there are difficulties in protection coordination in general for DC, right? So this setup is a TNS setup, again, according to the current OS rule, with a transformer isolated AC-DC. Yeah, so it's a simple, effective conversion for AC-DC to enable 700 volt DC. And it's protected by DC fuses and SSCBs. So the SSCBs is a current rotor. We name it a current rotor. It features a design-free selectivity for the loads connected. So this is important because we didn't really spend time on this installation to do all of these protection coordination. This is a cumbersome work that designers are usually rejecting to perform, basically, because it's sometimes it changes with all of these parameters that you would see along the project deployment. So the total coordination is easily achieved with the current rotor setup, and that enables us to scale up this system very conveniently. So basically, plug and play with more EV chargers in the coming days. The last part, the bullet that I want to share with you, is improved safety for equipment and operation and maintenance. For equipment, that's the true wording that Ronald mentioned about zone 3 and zone 4. So with the current rotor installed in our system, we enabled zone 3 and zone 4 in our work. And this, personally speaking, is a very convenient thing. This zoning concept is a very convenient thing for myself, in between myself and the operating team on site. This is very important because people would know the risks. It implies the risks that the operating personnel needs to be aware of when they are operating such a system. So with zone 0 and zone 1, they would already know that, hey, you guys really need to take care, because everybody with a power background would know that a 20 kiloamp steady state or a peak fault level would be significantly different from something that is around 100 amp, let's say. So with microseconds. So the fault energy level is totally different. And the operating team would know it and imply it as a risk assessment by themselves. So this is very important for operating team. The last one is a little story that we see during our commissioning time. We had these street lights deployed on 350 volt, and you all know that with street lights, with lighting poles, are subject to very humid, sometimes very humid and complex environment within the pole itself, right? Within that limited diameter. And the wiring are really hard to see properly done. So during our commissioning, the residue current detection functionality, which is embedded in our converter for the street lighting, actually help us to detect the installation defects. So it triggers alarms for us to actually know where would be the problem. So these are the parts, that major takeaways that I wanted to share with you today about the experience running current OS. So thank you, and hope you have a overview on such an application. And if you have questions, I would take it in our chat. Thank you.
Thank you, 𝘁𝘁. So here you can do how you can join the current OS. And Raphael will send that link in the chat, and you will see what are the channels to join it. And yeah, so there will be an international conference on diesel microgrid in China also in this June, and also there are some. If you have that kind of digest, you can send the message to the link here. You can see in the screen. Okay, there are some highlights for this ICDCM mission. We will include DC system topics about the system technology, power electronic technologies, and the existing emerging DC application and other technologies. And then we don't have so much time, and I saw we have some questions in the chat, and some of them is already being answered by Roland or Marco. And I see some it's not yet. So maybe we just take 1 minute. So for example, what Sugat has meant, why it is more difficult to separate touch a matched AC plus DC grid, unlike a linear AC grid. So I'm not sure, Marco or Ronan, can you answer the question?
Yeah, hello. I can take one question related, let's say, to the capacitances in the systems. Of course, it is not only are not always available in terms of exact value of the system. The important thing is to have at least the architecture of the system with the number of converter and at least the rated power of each converter. And we can assume a sort of maximum value of capacitances. Usually they are also order of millifarad, in order at least to understand which could be a sort of derivative of the current by, let's say, calculating the second order equation in our system, in order, let's say, to understand which is the current derivative, maximum current derivative, and according to that, we can design and select the proper solid state. The other question regarding the 700 system with low inductance. Here, we have also to select the circuit breaker having the right capability, let's say, to switch off, let's say, basically the system with the existing inductance. So if it is not, let's say, easy or enough, in some cases, we can add an additional inductance inside the circuit breaker or also outside in order, let's say, to limit the current derivative to the maximum that the circuit breaker is able to interrupt, or selecting another version of the circuit breaker having the right current derivative. I guess the next one can be taken by Rona regarding the cybersecurity.
Yeah, I don't think this is really a question. I think Wasif is, yeah, it is more agreeing upon that the cybersecurity in DC microgrids is more resilient compared to AC, and indeed because of the decentralized power management. You do not need communication already on that level to do power control, power management, and that is indeed one big advantage of a microgrid.
Then the last one, I guess still for you, regarding the intertripping wire. I guess it's a long explanation regarding the intertripping wire function.
The intertripping wire, in our system reference document of current OS, there is a requirement and specification of intertripping. It's, by the way, also on the MOOC indeed. But intertripping is currently developed in Joint Working Group 44 in the prosumer electrical installation IEC group, Joint Working Group 44, where I was referring to before, and it will be in the next revision. But also in current OS, we have already a requirement and specification out of that. If you are especially interested in that, you can reach out to me and I will send you what we have for the moment.
Okay, I think we are running out of time. I think it's time we need to close this session. And thank you everyone to join us. And also my sincere thank you to all the speakers for your preparation and also answering of the questions. And so we all thank you for your joining us, and we also very happy that we have this kind of strong participants from different sides. And we hope to see you soon in the next webinar. And in the meantime, if you have interest, you can contact us by the link Raphael just sent out and also the website. Okay, thank you very much. Looking forward to see you.
Very much.
Thank you. Goodbye.
Bye.
Thank you.
Bye.
Goodbye.
Bye.
Bye.